Okay, why don't we start? I'll keep it brief. Welcome to the session preview on type theory. Really pleased to have Max New tell us about the 3 papers that'll be presented later today.
Okay. Mic's working? Great. Great, yeah. Thanks for running up here for the session preview before you now run back for the next sequence of talks. I'm going to talk about these 3 papers from the type theory session. And I'll point out first of all, we have a distinguished paper in this session, which means the PC wants you to be at this session and read this paper and also the other 2 papers. I'll give this session my Distinguished Session Award, and so you should all go to it. Okay, so what is type theory? All right, so type theory is really the mathematical logical foundations for proof assistant tools that we know and love, right? So the proof assistants that we're all familiar with, things like Isabelle Hall, Coq, Agda, Lean, others, right? They are all based on mathematical logics, what we call type theories. And here are the examples for these 3. Isabelle Hall based on higher order logic, Coq, calculus of inductive constructions, Agda, Martin-Love type theory. And so in type theory, we study these mathematical foundations. And so what do we do in type theory research is we try to extend these type theories to add new features, right? And so in these 3 papers, they all extended some of these systems with new features that I'm going to talk about a little today. And so how do we evaluate these new features? Well, on the one hand, we want them to be useful for proving things in our proof assistant verifying programs. So they should make our proofs shorter, easier to write, more concise. But on the other hand, we want to make sure that they don't make proving things too easy so that we could prove absolutely anything like false. So we need to justify them by soundness theorems. So things like semantic models or translations into other existing systems that we already believe to be sound. Okay, and so the first paper, which is the one with this Distinguished Paper Award, is admissible types to pers relativization in higher order logic. So what is this one all about? So the first thing you should know if you're not familiar with is that the system Hall is based on simple type theory rather than a dependent type theory. Okay, and so that means that so the advantage of this is it's a very simple system to implement. It has a very small implementation that's easy to vet for correctness. But one of the disadvantages is there's a lot fewer type formers in this language, okay? As compared to something like dependent type theory, where we have a lot of formers and it's complicated to implement, okay? So one of the things that we have is that since it's based on simple type theory, we can define something like the type of all functions from alpha to alpha, right? That's a simple type in simply typed lambda calculus. But something we might want to talk about, such as the set of all bijective functions from alpha to alpha, is not definable as a type in higher order logic. Okay, so there's no corresponding kind of set comprehension construction here. Okay, and so, but what we can do when working in higher order logic is to break these up into 2 parts and say, well, we can just carry around both the type, in this case alpha to alpha, and a predicate on it, such that the elements are bijective, for instance. And then we can work directly with these type predicate pairs. And what we'll do is we'll take statements in the theory that use types, and such as, we have alpha as a type, and then we have some statement like saying addition is commutative. Some addition operation is commutative. So we would say for all x and y in alpha, x plus y equals y plus x, right? But then if we wanted to instantiate this alpha with something that wasn't a type, but was instead a set, we would have to add additional assumptions everywhere every time we use it. So instead of saying for all x in alpha, we would say for all x a type alpha, but also satisfying this additional predicate A, et cetera, et cetera. And when you get to even more complicated statements, the translation gets even more complicated. And so they call this process relativization. And what they did is they implemented this as an automated process. And it turns out subsets alone don't work, and they have to move to something more powerful called partial equivalence relations. And it justifies an addition that was made to Isabelle Hall in practice, a local type definition that's basically a form of the subset types. And they show that it's sound by translating it from the extended system into the system without this additional feature. So it shows that they can still stick to the small core, but get some of these nice benefits. Okay? So for the next paper, which we have some authors right here, we have an order theoretic analysis of universe polymorphism. So what is a universe? So a universe in type theory, which are as U, is a kind of type of types. So if you've used Calc or Agda, these are things like set and type and sort of prop. And of course, this is very useful for programming. For instance, writing anything that's polymorphic over a type, right? So if we write a map function over lists, then we'll say for any A and B that are types, if I have a function from A to B, I can lift that to a function from list A to list B. Okay, and so what we would like is that we could quantify over any type whenever we wanted. So we would like for every type to live in some universe, but a problem is we can't just say that there's only one universe and every type is in that, including itself. That turns out to be inconsistent, which was actually in Martin-Luff's original type theory. And so the solution is to introduce some kind of hierarchy of universe. Instead of just one universe, we'll have many universes that are related to each other. For instance, we might have each universe UI is a member of the next one up, UI plus 1. But then in solving this inconsistency, we've introduced a new problem, which is now every time we're going to write a function that uses universes, we have to say which universe are we working in. So, so if we take our map function, right now we would say, okay, for all A and B at a particular universe UI, right? And so universe polymorphism is how we're going to work around this issue, which is that we're going to write functions like map, where it doesn't really matter what this universe level is, okay? And so universe polymorphism is hard to get right, and there's not really an agreement, I would say, between the different communities about the design. So Koch and Agda use different approaches. But there was an approach introduced by Connor McBride, unpublished, I think, which he called crude but effective, which kind of grew out his frustration with the way that other people were doing things. And it turned out to be simpler to implement, but maybe cruder. But the lesson of this paper is that crude but effective is actually just as good as anything else. So the way that they show this is they develop a very general notion of universe hierarchy, and they show all of them are sound. And they show that all of these embed into what they call these displacement algebras, which is an abstraction of this crude but effective method. So it's crude but effective and also universal. Okay, and then our last talk, we have impredicative observational equality. So the point of this paper is to introduce a type theory that combines two very strong logical principles that have been shown difficult to combine in the past. So an impredicative universe of propositions and this uniqueness of identity proofs principle. And so what is impredicative quantification? So impredicative quantification for a type of propositions says that when I make a for all quantifier for all x of type A, such that B of x, it doesn't matter what universe level this A is in. The thing that I get out is a normal proposition, as opposed to a predicative system where when I do this quantifier, since A is big, the type of this quantifier overall has to be big as well, okay? And so I'd say normal set theory works this way. And so this is a very powerful logical principle. For instance, you need this to prove normalization of system F, something very standard we would see at POPL'. And it's also just convenient. You can avoid proliferation of universes. And on the other hand, we have this uniqueness of identity proofs principle, which here it is literally, which says if I have two different proofs, P and Q, that A equals B, then in fact those proofs are equal. And so what the hell does this mean? Well, it basically says math works like normal set theory does. And when I don't have to think about when two different proofs are equal. And in particular, the Koch type checker wouldn't have to care about whether two proofs are equal when checking two terms are equal. Okay? And so prior work had shown that if you add impredicativity if you add uniqueness of identity proofs to, for instance, Coq, which has an impredicative type of propositions, then it breaks Coq's normalization algorithm, and so breaks the existing implementation. And so the fix in this paper is to use a slightly different form of the type of propositions, which is a proof irrelevant, definitionally proof irrelevant type of propositions. And so they show in this paper that they get out decidable conversion, which means that you could actually implement the type checker. They give a normalization procedure, and they justify it also with a set theoretic model to show that it's sound. Okay? And so, again, this is my distinguished session of POPL, so I hope you get over there, check out these nice talks.
Thanks, Max. It's a really hard problem to present other people's work in 10 minutes. And this is in a particularly technically challenging session. So thank you so much for a great talk. Thanks. And now run downstairs. Thanks, everyone.